So welcome back to our next video where we are going to talk about natural vibrations of a spring mass system. So in this experiment mainly we will be calculating a body's natural vibration by calculating its natural frequency. Practically natural frequency calculation is very important for any body practically going into any application, because a frequency is a very important matter for a subject, because if we match the natural frequency of that object, maybe that body or that object may lead to its application failure and can turn into a disaster. For an example, we are going to take a windshield of our car. The car we use, they all have a windshield over there. All the glasses used in those windshields are practically tested for its natural frequency. Why is it important? Why are we testing its natural frequency? Practically natural frequency mainly occurs due to its repetitive vibrations of an internal object only. Just like in the car, engine vibrations are there, road vibrations are there. Those are all repetitive characteristics due to which vibrations occur in the glasses. So practically for a glass used in the windshield application, the vibrations frequency should not match the natural frequency of that glass. So these all things are taken into consideration for calculating the natural frequency of a glass. So to determine the natural frequency of any object, so then in this experiment we will be finding out how to take it out. So let's head on to the experiment.
Okay, it is really essential to find the natural vibrations of a system, like in case of suspension bridges and windscreens. Due to the natural vibrations of the engine, in case of windscreen it can break, and in case of suspension bridge it can collapse. So this experiment is done to find the natural frequencies of this beam. There are two parts in this experiment: part A, which is used to measure the spring stiffness, and part B, which is used to find the natural frequency of this beam. So for part A, the apparatus is weights, scale and spring, and the mass exciter position. So place the exciter to the rightmost place, and we need to find the initial position of the spring. So it is at 14.1 centimeter. Then place a mass of 0.5 kg near the spring and find the deflection in the spring. So the deflection is 15 centimeters. So we need to find the change in the length of the spring, which is 15 minus 14.1. Then increase the weight to 1 kg and observe the deflection in the spring. This time the observation is 15.6 centimeters, and then again increase the mass to 1.5 kgs and observe the deflection. Here it is 16.6 centimeters. So tabulate these readings and find the natural stiffness of the spring. In order to find the natural frequencies of the beam, we need to place the exciter a little bit far from position A and measure its length. We should measure the length of the center of the exciter to the center of the support. Here we can observe that it is 16 centimeters. We should also ensure that the length should not exceed more than half of the length of the beam, as it will change the spring stiffness. Then after placing it at 16 centimeters, we should deflect it and measure time for 10 oscillations. So here it is 3 seconds. Again, change the position of the exciter and measure its length from the support. Here we can observe it is 20.5 centimeters. Repeat the same and measure time for 10 oscillations. Here it is 3.94 seconds. Fill in the table and you can find the natural frequencies with experimentally. Also, using theoretical formulas, you can find the theoretical frequencies and compare both.
So as we can see in our tabular column, first we will find out the initial reading of the scale. Then we will add mass by 0.5 kgs, and we will get the deflection. And by using the deflection and by using the formula, F by deflection equal to stiffness. We will calculate the stiffness. Similarly, we will carry out the experiment 3 times and we will get spring stiffness 3 times. Then we will take the average and we will use this average in our next tabular column. So in our second table, we have to put exciter away from the pivot position and we have to calculate that distance, and then we have to take time for 10 oscillations, and by this we can use the formula for experimental frequency, which is 10 by t seconds. The second we will get from 10 oscillations, and similarly we can use the formula for theoretical frequency, which is 1 by 2 pi under root k by m. So by this we come to the end of our experiment. Hope to see you soon in our next video.